let's get ready for our third session and third talk of the day. For this one, I'd like to bring on Uma from Succinct to tell you about all the things that they're doing with SP1. So please give Uma a big round of applause.
My name is Uma. I'm one of the co-founders of Succinct. And today I'm going to be talking about ZK, what we're doing with SP1, and some cool hackathon ideas that you can build on top of it. So let's start off with a very high-level overview of what ZK enables. It's obviously a very popular term and buzzword, and it's often made out to be pretty complicated, but I actually think there's a way to talk about it that's very simple. Fundamentally, in ZK systems, you have a prover that wants to prove that when you do some sort of computation on a certain set of inputs, that you get a output. So they generate a proof that when you run a function f on a series of inputs x, it results in an answer y. And then the verifier can verify the proof and then accept it or reject it. And critically, ZK has this succinctness property where verifying the proof of the original computation is a lot more efficient than re-executing the computation. So that's the succinctness property and also what our company is named after. Now, the other cool part about ZK is the zero knowledge part, where you can basically hide the inputs to the actual computation. So this is important for use cases like privacy on chain that I'll go into a little bit. And this is kind of like the magical part about ZK, is that you can prove a statement or a computation has a certain answer without even revealing what inputs went into it. And that's the part that people find very magical, and it has a lot of interesting math as to how you actually accomplish this result. So in the context of blockchains, let's talk about why ZK is powerful and necessary. So the first property, the succinctness property, is really important for scalability. Intrinsically, you can think of in decentralized systems, there's an inherent overhead because you have all these nodes across the world re-executing transactions and verifying the results and making sure that the balances are computed properly. So there's overhead from this redundant computation. Now, in a ZK world, you can basically have those nodes verify proofs of the computation, and they don't have to re-execute them. And that's how we scale all these blockchain systems. And in particular, Ethereum's rollup-centric roadmap really embraces ZK as a kind of solution to having decentralized systems that scale but are still verifiable. And there's a bunch of topics in the Ethereum ecosystem that a lot of people have been talking about recently, like fast finality, interoperability across all these rollups, unified liquidity, bridging, that will be solved by adoption of ZK in the Ethereum stack. The other thing ZK is useful for in the context of blockchains is privacy. So today, in systems like Ethereum or Bitcoin, they're fully transparent ledgers where you can see what the history of what all accounts have done. And with ZK, you can now hide the inputs to transactions, and you can enable privacy on chain while still preserving verifiability. So for example, take systems like Tornado Cash, where you can hide the recipient of a transfer. Now, ZK is also powerful outside of blockchains, and that's also a big area of interest. So for example, those two same properties, privacy and verifiability, can help systems outside of Ethereum or Bitcoin or the blockchains we know. So just to go through some concrete examples that are talked about less in kind of these sorts of conferences that I still think are really interesting is today in Web 2 or any of the systems we interact with, if you want to prove in any sort of information to external parties, users are expected to reveal all their data. So to take a really concrete example, if you've ever done a rental agreement and your landlord wants to know that you have enough income to cover your rent, you have to provide your entire bank statement and income history, which is very invasive. You could imagine with zero-knowledge proofs, you just provide a proof that your income is above a certain threshold to your landlord, and they learn the information that they need to know without revealing any extra details that you might want to keep private. Similarly, for proving age, on any internet system, you have to provide all the details of your driver's license or passport, and with ZK, you could just prove that my age is over 21 or over 25 without revealing your exact birth date. And then finally, whenever you want to log into a system and prove that you have some sort of Twitter account or any other social media account today, you have to actually provide access to your entire Twitter account and reveal exactly who you are. But you could imagine that people want to include Twitter accounts in just a set And you wouldn't have to reveal that you're a particular Twitter user. You could just reveal you're in a set of accounts that are approved in a ZK future. Verifiability is also pretty interesting. So today, you have a lot of these agencies that have regulatory compliance, but they have no true verifiability. So to give a concrete example, in a credit scoring agency that determines people's credit scores, which is super important for use cases like getting a mortgage or determining your interest rate, today they can just update your credit score based on whatever information they want. There's no true accountability other than the government regulators stepping in. But in a ZK world, you could imagine that instead, these credit scoring agencies, every time they update your credit score, they have to provide a proof that it was done according to a certain ML model that's fair and not racist or sexist, and also is an ML model we all agree upon that does correct stuff, that has like the proper inputs according to your loans or whatever other information goes into updating your credit score. So there's a bunch of examples today where instead of having regulators having to spot check these agencies, they could use verifiability to ensure that they're doing things properly and in a fair way. So that's kind of the use cases of ZK. And then now I'm going to talk about what we're building at Succinct, which is a ZKVM that makes ZK really easy to use. So what is SP1? It's our ZKVM. It's a really fast ZKVM. And it enables any developer to use ZK by just writing normal Rust code. So how it works underneath the hood is you have an SP1 program that is just normal Rust. It compiles to this ISA called RISC-V, and then we generate a proof of your program with certain inputs using a bunch of cryptography and math that I won't go into. And at the end, you get the proof of your program with some inputs, results in some output, similar to my first slide where I outlined what does ZK at a high level look like. So that seems pretty straightforward and simple. You write some program or computation that you want to prove, and then SP1 helps you generate a proof of it. But I'm going to talk about why SP1 is super awesome. And for that, we have to go through the old way of doing ZK. So SP1 seems very intuitive. You just write your program in normal code. But the old way of doing ZK was not this at all. Basically, in the old way of ZK, and I have some screenshots that look pretty scary, and that's because the old way of ZK was very difficult, you had to write these things called circuits, where you write your computation that you want to generate a proof of and break it down into very low level, almost like assembly, additions and multiplications that we call a circuit. And you had to learn all these specialized languages and DSLs to actually do all this stuff, and often it ended up not being a very nice situation. You had to know a lot of math and cryptography. So in the old way of ZK, to do anything, you had to have a really big team that was really specialized with cryptography expertise to actually use ZK at all. And this had a lot of problems. Obviously, one big one is that you require specialized expertise, so it's not that accessible. Another thing is it's really hard to customize and maintain and upgrade systems, because every time you want to maybe do a new feature, you'd have to spend a lot of engineering effort to add it to your system. Also, auditing these systems was really difficult because it requires a lot of specialized expertise, and it's all very complicated. And then in general, it was also expensive and hard to implement generic applications with this old model of ZK. And then with SP1, though, because you can just use normal code, anyone can now use ZK. And you can actually prove basically any statement that you want. So this is an example of the SP1 program, and for those of you who are familiar with Rust, this is computing the nth Fibonacci number in SP1, which is kind of the hello world of ZK. And you can see that it looks just like totally normal code, and it's all very simple. You don't need to understand any of the math or any of the cryptography. And so that's why SP1 is super awesome. You can just write normal Rust. You can reuse existing libraries from existing software stacks and really build anything with ZK and be any developer. You don't need to know any advanced math. So SP1 is also kind of a breakthrough because it has really fast performance. And so on our team, we did a lot of novel cryptography stuff to make SP1 really fast. So in particular, one of the biggest use cases of ZK today is ZK Rollups in the Ethereum ecosystem, as I was touching upon before. And one interesting fact we noticed is that in the ZK Rollup paradigm, most of the ZK overhead is spent in really repetitive cryptographic operations like hash functions and verifying elliptic curve cryptography for verifying digital signatures. And so we introduced this system that we call our precompile-centric architecture, where there's a way to have specialized circuits for those really intensive operations that connect to our main RISC-V CPU prover and accelerate everything by an order of magnitude. So SP1 is basically the fastest ZKVM by an order of magnitude, especially for these rollup and blockchain use cases, because of this precompile-centric architecture that philosophically you can kind of think of as ZK native assembly. We also implemented an optimized GPU prover that helps improve the cost and latency by another order of magnitude. And then we have a bunch of other algorithmic optimizations in cryptography that makes SP1 really fast, especially for these blockchain use cases. So now that I've kind of covered ZK, what it's useful for, and then also why SP1 makes ZK easy and is super fast, I'm going to kind of go through a bunch of applications that I'm excited about that we've built with SP1. So as I was talking about before, one of the biggest applications of ZK today is ZK Rollups. And in the Ethereum-centric roadmap, for those of you that are familiar, there's kind of this world where every rollup in Ethereum is going to be a ZK rollup. And so with SP1, we were able to take Reth, which is a Rust implementation of an Ethereum client, and we were able to stick it in SP1 and run it. And there's the actual program that actually implements a ZK EVM in SP1. And in 1,100 lines of code, which is actually a very small amount, you're able to make a full ZK EVM that verifies Ethereum blocks and Ethereum transactions using SP1 plus the Rust implementation of Ethereum in a weekend. So that's pretty awesome, and that's something we put out there. And one really cool thing, just to give some numbers on SP1's blazing fast performance, is if you look at executing real Ethereum blocks, you can see that the proving costs per transaction are really cheap. In this case, you can see that on average, the proving cost per transactions between 0.1 to 0.2, sometimes 0.3 cents, which is really very little. And this kind of demonstrates that with SP1 today, ZK is not only really easy to use, right? You just take Reth, run an SP1, but it's also really cheap and really fast and practical. Another thing we recently did with SP1 is we took the OP Stack, which is a really popular rollup framework on Ethereum, and then we took their state transition function, which is what's needed to make the OP Stack rollup actually be settled on Ethereum, and we ran it in SP1. And what this lets us do is it lets us convert any OP Stack chain to a full type 1 ZK EVM with a really simple integration using the power of SP1. And that's the repository for it. So it's related to the previous work of running Reth and SP1, and in this case, it's taking an existing, very popular rollup framework that rollups like Base use, if you guys have heard of that, and taking it and making it into a full ZK rollup. And then finally, another big category of work we've done is we've made ZK-like clients with SP1. So in general, today, there's a really big problem of you have all these different chains, Ethereum, Solana, a bunch of Cosmos chains, and moving money and interoperating between them is a really big challenge. And ZK helps solve that because you can verify the consensus of one chain in the execution layer of another chain, and then you can have really trustless interoperability. And so we've built a bunch of ZK-like clients with SP1 to talk between Ethereum, Tendermint-based chains in the Cosmos ecosystem, and then even chains in the Polkadot ecosystem. And again, I have some code examples here that show with SP1, you can just import existing libraries like Tendermint or Helios, which is a Rust Ethereum-like client, and make all of these ZK-like clients in very few lines of code very easily using Rust plus SP1. So that's some of the stuff we've built with SP1, and that's kind of to show that, you know, those are the practical use cases. People are using them today. It's really easy. It's really fast. But now I want to talk about, since obviously there's the ETH Global Hackathon coming up this weekend, what are some other ideas for things we're excited to see being built with SP1? So the first set of ideas I kind of want to talk about is in the same theme of upgrading the current blockchain stack with SP1 and ZK, and kind of getting ZK everywhere it needs to be with it to help blockchains scale. So one interesting idea is you can implement new consensus algorithms in SP1 to connect more ecosystems. For example, we've already connected Ethereum and the Cosmos ecosystem with our Tendermint-like client, but there's a bunch more chains that could benefit from having ZK-like client implementations that would be pretty straightforward to implement in SP1. There's also a bunch of bridges these days that support modular security verification, and it would be really interesting to take all these ZK-like clients and actually integrate them into the existing bridge frameworks so that existing bridges can be upgraded to have ZK-like client security as opposed to the multi-sigs they have today. Another interesting project, not in the Ethereum ecosystem, but in the Bitcoin ecosystem, and actually I think someone has worked on this at a previous hackathon, is you're taking the entire Bitcoin chain and generating a proof of its state transition function and proof of work to basically prove the entire history of the chain from Genesis till now. And that would be possible to do in SP1. I think actually some people have done it in the past with the ZK circuit method, but it was very cumbersome and had a lot of complex code, and I think this would be relatively simple to do in SP1. And then in general, there's been a few talks. The talk by Rushi from Move 2 talks ago, talking about the Move VM, which is an alternative state machine that's not the EVM. And in general, there's been a lot of different state machines, Move VM, SVM, the Cosmos SDK, that can all be proven in SP1. And you can kind of imagine a future where every single blockchain execution environment is proven in a ZKVM so that they can all interoperate and have verifiability. There's some category of fun on-chain applications that can be possible with SP1. So one thing that's really cool about SP1 is not only can you just prove state machines, you can actually prove any piece of software. So for example, if you have a Rust implementation of a video game like Nintendo or Pokemon or Doom, you can take that code and run it in SP1, and now you can have provable video games that settle on-chain. So that's like a fun idea that I'm excited about. You could also imagine that you can have certain types of NFTs with really complex properties using ZK and SP1. So for example, you can make an NFT where you can prove that the art was generated according to some complex model. Normally that would be prohibitively expensive to do on-chain, but you can just write the Rust function for it, prove it in SP1, and then do a conditional mint based on the proof. And I think that's also a really fun idea. And another category in a related vein that I'm excited about is bringing ML models on-chain using ZK. So normally, it's very expensive to have things like MNIST or GPT-1 or GPT-2 or logistic regression on-chain. You also probably don't want to write that stuff in Solidity because there's no existing ML libraries in Solidity. But thankfully, because you can just take normal code in Rust and run it in SP1, now you can start bringing more pieces of software, and especially ML on-chain, that I think would also be pretty interesting. And then the last category of ideas that I'm excited to talk about is real-world ZK applications, kind of in the non-blockchain use cases of ZK that I covered in my first few slides. So one idea that I think is really, really cool that I would love to see built is attested image editing. Today, on the internet, if you go on Twitter, there is no telling whether an image was from a real camera or an iPhone or just made up by something like Midjourney or DALL-E. It would be very interesting to basically take the signature that signs an image. So if you have verifiable hardware that signs the fact that the image was produced from a real camera, the iPhone already does this today, you can prove that the image was generated from a real camera on real hardware and then transformed through cropping or JPEG compression to the image that you see that's being served on Twitter. And I think ZK will be a really important part of how we can tell authenticity of images and in general other data on the internet in the future. So that would be a very cool demo. Another thing a lot of people want to do with SP1 is they want to run it on their mobile phone. And no one's really done that yet. And that would also be really cool to explore. Like, can you take SP1, run it in Swift, or run it on an iPhone and see how it performs? There's some other really cool examples of taking Web 2 data and bringing it to Web 3. So for example, verifying emails or verifying passports in SP1 and bringing that data on chain. Today, actually, almost all emails are signed by a cryptographic protocol by the issuing name server of the email. So for example, if you get an email from Twitter, the Twitter public key for their email server will sign that email attesting that a real person from Twitter sent it. And you can verify that signature in SP1 and prove that you received an email from a certain source. You can also do the same thing with passports. Passports are signed generally by the issuing country and the passport authority, and there's a public key registry. So you can verify that, oh, I have a passport that's issued by the United States and reveal certain information, for example, to prove that you're a citizen on chain. So all that stuff would be cool to do in SP1. In general, I think there's potentially a lot of other sources of digital signatures across various different data sources. So emails and passports are just 2 examples. What are other areas that have signatures that we can prove in ZK and then selectively reveal information about and bring it on-chain, or also use it in off-chain context to selectively reveal only the information that we want to reveal instead of having to dox our entire identity. And then finally, things like PDF documents or taking images and running ML models on it, I think is also a really interesting real-world ZK use case where you can start bringing this data on-chain or even use it in off-chain contexts. So those are some of the examples of SP1 that I'm really excited to see built across a bunch of different applications and ecosystems. And yeah, hopefully that was interesting. If you're interested, this is my information, you can reach out. Those are the repos I mentioned. And yeah, in general, really excited to see ZK, now that it's much more accessible, get a lot more adoption and a lot more people building with it. Thank you.